In this video, we are going to look at the Unit 1B review for pre-calc. This is going to cover piecewise functions, transformations of parent functions, and combinations and compositions of functions. In this first one, we're going to look at writing a piecewise function for each of these graphs and then providing the domain and range. So when we're writing a piecewise function, you need to look at it as its different pieces of function. So you can hopefully see here that we've got three different chunks, and the chunks split at these two x values. And so I like to just start by getting the boundaries on there. So this is a boundary line of x equals 1, since we're counting by halves here. And this one's at x equals 2. And so that's going to help us with our domain of this function. And then we can see that there are three different pieces to this function. So we have the chunk on the left, the middle, and the right-hand side. And so I like to start by writing the domain, and maybe I'll just write out some blanks here so we can see the kind of three different pieces coming to place here. So if I'm writing the domain of this portion on the left-hand side, so if I'm doing this one, now I'm going to do this as an open circle. We've got kind of two functions that overlap here. So one can be an open circle and one can be a closed circle. So I'm just going to write this first one as an open circle. It doesn't matter. So this piece has all of the x values that are lower than this, and I guess this is -1, not 1. So lower than -1. And so my domain for this is x's that are less than -1. So now we need to write the equation for this. And you can do this in a couple of different ways. You can do slope-intercept form here, since it's linear. So you can do y equals mx plus b form. And in that case, you need the slope. So you can count kind of two different points on here and look at the rise over the run. So this is a rise of 2 and a run of 1, but it's going down. So our slope is -2. And then you would want to continue this pattern to see where it would cross the y-axis. So if I'm going down 2 boxes over 1, so down 2 over 1, down 2 over 1 would put us right here if this graph got to continue on. Okay, so if this, and let me just extend it this way, let me show you. So if this had a full domain, this would be crossing at a y-intercept of 1. So if I could think of extending the line that way, or like I did, you can count down 1 over 2 and you can get to that same spot. So this would be the equation of that graph in slope-intercept form. So -2x plus 1. And then usually we put an if here for if the domain is x's that are less than -1. So that's one way you can write a linear function. Another way you can do this, and it doesn't matter, you can choose either way, is by using transformations of the parent function. So if I wanted to write this using transformations, then I would just recognize that it's a linear function. Okay, so you can think of it as a times x minus h plus k. So I just have a linear, so I don't have any exponents or anything out here. If it was a quadratic, I'd have a squared, or if it was an absolute value, these would be absolute value bars. Okay, this one's just linear. So this vertical dilation right here is just going to be your slope. So remember that our slope was -2. And now you can look at where this point moves to and use that as your transformations. So this point is 1 to the left and 3 units up. So then if I want this to go 1 to the left, then this parenthesis would say x plus 1. And if I want it to go up 3, then we'd have a plus 3 on the outside. So you could also write your equation like this: -2 times x plus 1 plus 3. And that would be the same thing as the slope-intercept form. It just depends on what you like. Okay, so either of those are perfectly fine. Then for this middle part, the middle chunk of the graph, so now if you did an open circle, meaning you didn't put an underline here, now for this middle part, you'll want to do a closed circle. So I'm going to do a closed circle from end to end on this middle chunk. And this is constant. It's not going up or down. So this one is just a y value of 3. And then the domain for this is when your x's are between these two numbers of -1 and 2. So when -1 is less than or equal to x, and when x is less than or equal to 2, since I decided to do the closed circles on this chunk. Then your next one is another linear function. And now if you did a closed circle in the middle, then this one's going to be an open circle for this part. And so the domain here is the x's that are greater than 2. And then you'll just want to write the equation for this line. I'm just going to do the transformation form for this one. So if I look at the vertical slope or the vertical shift here, the vertical dilation, this is up 2 over 1. So my a value is going to be 2. Now this one shifted to the right 2. So this is going to say x minus 2 inside of the parenthesis. And then it's going up 3. So then a plus 3 outside. And that would be your equation there. Again, you can certainly do slope-intercept form also if you'd like. Then for the domain, we're looking at the fact that we have an arrow going to the left and we have an arrow going to the right, and there's no breaks in between this. So our domain is all real numbers, -infinity to infinity. And then our range is stuck here, okay? It gets stuck down here at this y value. And so it's only the y values from here and up, and this y value is 3. So that bottom y value for your range is 3, and it's a hard bracket 3 since 3 is part of the range, and then up to infinity. For graph B, we again have 3 different chunks here. And so we have this boundary line cutting it, and let me do a dotted line for that. So we have a split in the two functions here, not a split, but it separates the two functions. And then here as well, so I like to call those the boundary lines. These values are x equals -1 and x equals 3. Those will help us write the domain. And so again, we've got 3 chunks to this. So I'll just draw in 3 lines to help us. And so this left portion is a quadratic, okay? We can tell because of the parabola. And so this one you're going to want to write transformation form. At least I would like to do transformation form. It seems to be the easiest. So for this one, remember that you're going to have an a times an x minus h squared plus k. So this one, the a value, the parabola is upside down. So it was flipped over, and it's the same width as a normal parent function. So this one's just going to have a -1 outside the parentheses. So you can just write a negative if you'd like. Then this one was moved 3 units to the left. So the inside should say +3 squared. And then it was moved 4 units up. So then a +4 on the outside. So +3 inside so that it moves left 3, +4 outside so it moves up 4, and then it was flipped over so you should have a negative. And then this is for a domain that's less than -1. So this is all the values below -1. And again, this overlaps the middle chunk. So I'll just do this one as an open circle for this portion of the graph. And then for this middle portion, I'll do a closed circle. And so this middle chunk here goes from here up to here. And so this one is between those two x values. So it's between -1 and 3. And now I did closed circles on both of them, so I'll put an underline under the less than symbols. And this one's linear, so again, we can do the transformation form if we want to, or we can do slope-intercept. Since this one actually shows us the y-intercept, I'm just going to do slope-intercept form here, but you can certainly do transformation form. But we can see that it crosses the y-axis at +2, so we know our b value from y equals mx plus b, the b will be 2. Then you can just check the slope. So go to any other points that are on here and just count the rise over the run. So that's up 2/1. So our slope or our m value will be 2. So our equation's 2x plus 2. And that's again for if x is between -1 and 3. Then this final chunk of the graph is a constant. And now I'm going to do an open circle here, and then this one will continue forever. And so this one is for x's that are greater than 3. So again, you don't want a closed circle on 3 in 2 places. Otherwise, it wouldn't be a function. So one needs to be closed, one needs to be open. And then this one just has y values at 8. So this is 8 if the x's are bigger than 3. For the domain, again, we have one arrow going to the left and we have one arrow going to the right, and there's no breaks in this function. So this domain is going to be all real numbers. And then for this one, we have an arrow going down. Okay, so we have this down arrow, but then our function gets stuck here, so it doesn't go above 8. So for our range, it's going to be from -infinity all the way up until y equals 8, and it won't go past that. It will equal 8, so we'll do a hard bracket there, but it won't go past. Number 2 asks us to graph the piecewise functions and then answer the question. So for this one, we've got, again, 2 different pieces of this graph. And so I'll just graph this top one in blue, and then I'll graph this bottom one in this orangish red color. We do want to put the boundaries on here to make sure that we are graphing those, and I like to plot those in dotted lines on my graph. So we see that we have a boundary at x equals -1. And then in the second part, we have it at -4 and -1. So this just helps us to section off our graph. Then what I like to do when I'm graphing piecewise functions is just make a table for each part. So for this first function, we want x's that are greater than -1. So you want to start with the boundary of -1, and then you want numbers bigger than 1. And I'll just start with these ones and see if I need to do any more, if more will fit. So we'll plug -1 into the function. Okay, so we're going to be doing -1 squared minus 3. So -1 squared is 1 minus 3 gives us -2. Then we'll plug in 0. So 0 squared minus 3, that's 0 minus 3, which is -3. Then we'll plug in 1. So 1 squared minus 3, which is 1 minus 3. So that's -2. Plug in 2. So 2 squared minus 3. 2 squared is 4, minus 3 is 1. And I would say we can plug more values in here because this is only at 1. And our graph goes up to 5. So let's try plugging another x value in. So 3 squared minus 3. So 3 squared is 9, minus 3 is 6. And so then we wouldn't have any more to plot because that one actually went off of our graph by a little bit. So now when we go to plot these, we want to think about whether our boundary point is an open or a closed circle. So when we're looking at the boundary, we're looking at this. So this is just a greater than symbol. So this is an open circle when we plot this point. So at -1, our y value was -2. So we're going to go to -1, -2 and plot that point with an open circle. And then we'll graph the rest of these. So at 0, it was at 3. At 1, it was at -2. At 2, we were at 1. And at 3, we were at 6. So just off of the graph here. And then we know that this is a quadratic since it was a squared function. And so that makes sense that it's making this U shape. And then this one just keeps going on forever. So I'll put an arrow at the end here. So for all x's that are greater than -1. Then for the second piece of this graph, we're following the 2x plus 1 function. And this one is going to be specifically from -4 to -1. So those are the only points I'm going to put on here. So -4, -3, -2, -1. And we'll plug these into the 2x plus 1. So we'll do 2 times the x value plus 1. So 2 times -4 is -8, plus 1 is -7. Then 2 times -3 plus 1. And so that's -6 plus 1, which is -5. Then we'll do 2 times -2 plus 1. So that's -4 plus 1, which gives us -3. Then 2 times -1 plus 1. So that's -2 plus 1, which is -1. So then we can look here at the boundaries again. So at -4, we have an open circle. And then at -1, we have a closed circle. So then we'll go ahead and graph these. And so at -4, unfortunately, it's off the graph, but so it's going to just be below this graph. So you're not really going to see that on your paper. You could plot it down further and just kind of guess where -7 is if you wanted to. At -3, it'll be at -5. At -2, it'll be at -3. And then at -1, it's at -1 with a closed circle. So then we can just connect those down, and then that would be your piecewise function. So then for the domain, our domain is just from -4 and higher, because this is where it starts at. And -4 is not included in our domain since we had an open circle there. So we just have -4 to infinity, not including -4. And then is this function continuous? And that would be no, because at x equals 1, -1, you get 2 different values. Now, one has an open circle and one has a closed circle, but we can see that there's a split here. Okay, they're at different heights. So you could say it like that. You could say no, because there's a split in the graph at x equals -1. You could say there's jump discontinuity. So if we wanted to say because there's jump discontinuity at x equals 1, since there's 2 different height values, that's fine as well. Number 3, graph the transformation of x. So here's our f of x graph, and then we want to plot these different transformations. Now on yours, I think I didn't give you the right graph paper, so let me just put this on, because I think you actually have it with these on there. So let me put this on there so we can do it. So I can do it like it looks like on your worksheet potentially. So when you do this, so when you're doing transformations, this inside number, right, is a shift. So this is a horizontal shift. Since it says -2, it's actually going to the right 2 units. And then this outside number is a vertical shift. And this one does exactly what you think. So this one is a +3, so it's going up 3. So we're going to take every one of these points and we're going to move it 2 to the right and 3 up. And you're going to do this for every one of these points. You'll just count over 2 and then up 3. Now mine is going to do this all at once. Oh, no, it's not. Okay, good. So over 2, up 1, 2, 3. Over 2, up 1, 2, 3. Over 2, up 1, 2, 3. And then over 2, up 1, 2, 3. And then you can just connect those. Whoops. Okay, then on this next one, you actually have to do a vertical dilation by a factor of -2. Now you can do the negative as a reflection. You can also just multiply the y value by -2. And then we're going to be able to move it up 4. So what I'm going to do is look at this point right here, and its y value is at 7. So I'm just looking at the y value because both of these impact the range since they're on the outside. So when the y value is equal to 7, if I multiply it by -2, or sorry, not 7, it's at 5. So this is at 5 right here, right? So that's at 5. So that y value is 5. We're going to multiply it by -2. We get -10. So this one would flip down to -10. And then it's going to end up adding 4 from this last number. So then we'll add 4. So the new one will be at -6. And it's still going to be on this same vertical line. It's just going to be down here at -6. So then we can do that with the next point. So the next point has a y value of 1. Okay, so that y value is 1. So we're going to take it times -2, which puts us at -2. Then go up 4, which would put us at 2. So this one's actually going to move to 2 after we dilate it, reflect it, and move it up. This next one has a y value of 5 again. Well, we already know where that one goes. Okay, so that one ended up at -6 because it's going to follow this same pattern. This one's at 5 again, so that one's going to be at -6 after we do all of that. And then this last one, the y value is at 0. Well, we'll multiply that by -2, and that gives us 0. And then we'll vertically shift it up 4, so that puts us at 4. So this one's going to be up at 4. And then you can just connect those. But so the vertical dilation just multiplies the y by that number. Problems 4 through 9 are dealing with different functions and different operations. So remember when they're written like this in number 4, what this just means is you're doing g of x minus k of x. That's just another way to write it when you just write g minus k of x. So we're going to be taking the g function, okay, which is this one, x squared minus 4. And then we're going to be subtracting the k function. Now be careful when you subtract because you want to make sure you get parentheses around that second function so that you distribute that negative in. So we have minus the k function, which is 5 minus 2x. And then we'll simplify. So we have this x squared minus 4. Then you're going to bring in the negative. So you're going to be minusing 5 and then minus a negative 2x, which is plus 2x. Then you can combine your like terms. So we only have the x squared term. We only have the 2x. And then we have the negative 4 minus 5, which gives us negative 9. For number 5, you're just dividing the functions. So this is, again, just like h of x divided by g of x. And so our h function is this one. So we just have the square root of 16 minus 3x. And then our g function, again, is the x squared minus 4. And we wouldn't simplify that. We would just leave it like that. So that's your final answer. When you see this open circle here, okay, this means g of h of x. It means that h is going into g because h is on the inside. So h is going into the g function. So what I like to do is start with the outer function, okay? So the g is my outer function. So I'm going to write that down, but without this x. I'm going to have parentheses in that input. Okay, so here's my g function. It's something squared minus 4. And what's going into it instead of x is the h function. So h of x is going into g. So h is going into g. Then you can simplify. Now in this case, our square root on the inside is over the entire inside, and then we're squaring it. So those are going to be able to cancel. And we're going to get 16 minus 3x minus 4. So then we have like terms of 16 and negative 4. So we have the negative 3x, and then 16 minus 4 is positive 12. So then that would be our final answer. Now in these next 3, we're actually plugging in numbers into the function. So up here in 4 through 6, we had a variable. So we kept the equation or the expression. We had x's in each of our final answers. In these next ones, we're plugging in numbers. So we're going to have just a number value as our answer. So for number 7, we're plugging into the h function. So we're doing h of 2. So instead of x, we'll be putting a 2 in. So we have the square root of 16 minus 3 times 2. So the square root of 16 minus 6. So we end up with the square root of 10. So h of 2 equals the square root of 10. For the next one, we'll be doing g of 3 divided by f of 3. So we want to plug 3 into each of the 2 functions. So we'll plug 3 into the g function on top. And our g function is x squared minus 4. So in this case, 3 squared minus 4 on top. And then on bottom, we're plugging 3 into the f function, okay, which has a fraction in it also, okay? So we're doing 3 times 3 minus 1 over 2 times 3 plus 4. So then you can just simplify these separately, okay? So you've got the top, which 3 squared is 9, and 9 minus 4 is 5. Then on the bottom, you have 9 on top. You have 9 here minus 1, so that's 8. And then the bottom of this one is 6 plus 4, which is 10. You can use a calculator to do this if you want to. Otherwise, I'm going to write this as a division symbol. So we have 5 divided by 8/10. And so then we can change this to multiplying by the reciprocal. So we'll multiply by 10 over 8. And we end up with 50 over 8. Both of those divide by 2. If you wanted to simplify the fractions, you could get 25/4. Or if you used your calculator, you would just get 6.25. Then number 9 has us doing k of g of 0. So we're going to look at g of 0 first. Okay, so this inside part here is g of 0. So I'm going to do what g of 0 is. And g is the x squared function minus 4. So 0 squared minus 4. So g of 0 is 0 minus 4, or negative 4. So I know that g of 0, this whole part right here, is equal to negative 4. So ultimately what I then need to do is k of negative 4. So now we're going to go to the k function and plug in negative 4. And the k function is 5 minus 2 times x. X in this case is negative 4 again. So then k of negative 4 is equal to 5 plus 8, since negative 2 times 4 is positive 8. So k of negative 4 is equal to 13. So the final answer is 13. Numbers 10 through 13 asks us to use the graphs of f and g. So we have f over here, and then we have g over here. So when we're looking at this first one, again, we're just doing f of, whoops, let me do that in the other color. So you're just doing f of 3 here. And then you're adding g of 3. So when we go to look at f of 3, the 3 is your x value. So you're looking here at 3, and you're looking for where the function is at on that line. Okay, so at x equals 3, our function is at negative 2. So f of 3 is negative 2. And then we're going to add g of 3. So then we're going to go to the g function and again look at x equals 3. So here's x equals 3. Your function is here at 1. So g of 3 is 1. We'll add those together and we get negative 1. Next one, you're doing f of negative 1. Okay, because we're just plugging negative 1 into each of these. So we're doing f of negative 1 minus g of negative 1. So look at the f graph. And at x equals negative 1, the function is at 1. So f of negative 1 is 1. And then we're going to subtract g of negative 1. So then we'll look at the g function at negative 1 is at negative 1. And we'll subtract those. So 1 minus a negative 1 is 2. For number 12, we're doing g of f of negative 2. So we're looking at f of negative 2 first. So we're doing this part first. You start with the inside and work your way out. So when x is negative 2 on the f graph, the function is at 0. So f of negative 2 is 0. So this whole thing right here was 0. So now we'll plug 0 into the g function. So we'll do g of 0. So at x equals 0, the function is 0. So our final answer for number 12 is 0. Then in number 13, you're doing f of g of 1. So this time you're starting at the g function and looking at what it is when x equals 1. So on this g function, when x equals 1, y equals 1. So this whole thing right here was 1. So now we'll be doing f of 1. So we'll go to the f function and look at x equals 1. That equals 2. So then the overall of f of g of 1 is 2. Then the last one has us looking at a couple different functions here and just answering a couple questions about it. So I'm just going to highlight the f function here so that it stands out to us. So the f function is that blue one. So in part A, they want us to tell where the functions are equal. So this just means where they cross each other, okay? So when x equals 10, both functions equal 1. So we just want to name the x value of 10. That's when the functions are the same. For B, we want to know when g of x, that function in black on my screen, is equal to 0. And that means when it crosses the x-axis, because that's where the height is 0. So for the g function, that's here, 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 and here. And then we can just name those x values. So that's at x equals -6, 0, 2, and about 9.5. Then it wants us to name all of the places where the g function is greater than 0. And remember, this is your 0 line. So where is your g function above that? So now these ones are going to be intervals because it's going to be from here to here. So from x equals 0 until 2, the function is above the x-axis. And then again, from 9.5 to 11. Okay, so then again, from x equals 9.5 until 11, it's above the x-axis. So then when is it below 0? When is the g function below 0? Well, that's down here in these two chunks of the graph. So that's from an x value of -6 until 0 for that first chunk. And then again, from 2 until 9.5. Then finally, what are the intervals where f of x is above g of x? So f of x is above g of x here until they equal. And remember, they were equal at 10. So f is above g from -6 up until 10.